We are happy to have today Paul Seidel, who will speak about Fukaya categories for Calabi-Yau hypersurfaces. So, Paul, please.
Thank you very much for inviting me. I have to say, still haven't really made my peace with Zoom talks. As I propose, when this is all over, that we gather joyously and burn down the Zoom headquarters in a friendly way. Now you can all think whether I just committed a federal crime of inciting violence across state lines. Okay, so talking about Fukaya categories, right? So, ignoring the complicated details that go into defining a Fukaya category, one of the things that you notice immediately when you define it is this formal parameter Q. Okay, so this is, the string theory people call it a Kaehler parameter, and the symplectic geometers call it a Novikov parameter. Okay, so the way that it usually appears is that you have the symplectic form or Kaehler form, and you integrate it over some 2-chain in your manifold, and you get a real number, and you get this exponent here, okay? Which is also, if you are in a sort of more physics mood, you could write this as, okay? So we can think of this as a scaling parameter for the symplectic form. Okay, so if you like, you could say, oh, the symplectic form could be like this. It's minus log Q omega, whatever that means. And so if Q goes to 0, means what they call the large volume limit, omega Q goes to infinity. And the reason why I put this minus log Q is because this is in the exponential here. Okay, so it's equals e to the minus the integral omega Q. Okay, and so the consequence of this is that the Fukaya category is defined over some field, let me call it K, which is a field of series in Q. So let's say let's say the coefficients are various versions, but say the coefficients could be complex numbers, the exponents could be real, and they're infinitely many, but the exponents go to infinity. So it's some kind of version of a formal power series. So this means that every time you want to compute something in the Fukaya category, composition of morphisms and so on, in principle, it's given by some matrix whose coefficients, whose entries are these kinds of power series. So it would be nice to know what series actually occur. Okay. One reason is simply because if you just say it's an arbitrary series, each power series carries an infinite amount of information. That makes it very hard to figure out what information is the whole category as a whole has. The other reason is because maybe you're expecting some properties, such as convergence for small values of Q, as opposed to being just a formal power series. Actually occur, has to be interpreted with a little bit of care. Otherwise, it doesn't make too much sense. Okay, so note that objects of the Fukaya category are, roughly speaking, Lagrangian submanifolds. This is not exactly true, but I'm trying to make a point here. Lagrangian submanifolds with, oops, sorry. So this is K greater or equal to 0. So these are these series in Q. But this time here with the MI is greater or equal to 0, local systems. So there are a lot of objects, and because you can put in this gigantic ring of series is part of the definition of objects, you can't expect, so therefore, you can't expect all objects of the Fukaya category to be defined over a significantly smaller field, because there are just too many objects. Now, that just means that we haven't really asked the question properly, right? So if I give you, a complex elliptic curve, and I say that elliptic curve is really defined over the rational, that of course doesn't mean that every complex point on that elliptic curve is defined over the, is a rational point, right? It just means that, there are enough objects defined over the rationals to sort of, constitute a picture of that elliptic curve. So in order to see how this, so basically, you have to be a little bit careful about what you say to be defined over a field for a category. To explain how this works out in this particular case, I have to be a bit more specific about the geometry and about Fukaya categories and so on. Okay, so more concretely. So I should say, but, okay? There's something that can make more sense. Okay, more concretely, I want to consider a particular kind of Calabi-Yau manifolds, okay? So start with a Fano variety which carries a Lefschetz pencil, so a pencil, a non-degenerate pencil, a Lefschetz pencil of anti-canonical hypersurfaces. Okay, so this is always kind of useful. So you write, so let's say, so M bar, for reasons of my own, this notation is a little bit messed up, okay? So one hypersurface in the pencil. And this is what I'm actually interested in, the Fukaya category of this M bar. So this is a Calabi-Yau, right? The pencil, also the hypersurfaces in a pencil, they all intersect each other. So there's something here, called it delta M. So this is the base locus of the pencil. So this is, by definition, this is an ample divisor inside M bar, and you can look at its complement. Okay, so this is now an affine Calabi-Yau. Now the advantage of this Lefschetz pencil situation is that there is a particularly simple class of Lagrangian submanifolds. Okay, so Picard-Lefschetz theory gives rise to vanishing cycles, what's usually called the basis of vanishing cycles, which are Lagrangian submanifolds, which is called an L. They lie in this affine part of the fiber. Okay, and so instead of looking at the whole Fukaya category, I'm going to look at this one here first. Okay, so and I'm going to call this B to be the part of the Fukaya category of M. With objects L1 up to Lm. So this is defined over the complex numbers, because this is M. M is an affine Calabi-Yau, so the cohomology class of the symplectic form is 0, there is no actual Kaehler parameter. Now, the Fukaya category of M bar, which is the Calabi-Yau, actually has a Kaehler parameter. You can think of this as a deformation problem. So it's a deformation of B obtained by working in M bar, but still with the same objects here. So this is now defined over C double bracket Q. It's a little bit simpler because we just count. So we passing from M to M bar is adding this ample divisor delta M, and you just count the intersection number with this ample divisor. That's essentially your area. Okay, but how is this related? So if I extend coefficients to K, then this embeds fully and faithfully into the ordinary Fukaya category. Okay, so this is the standard Fukaya category. Okay, and this induces equivalences of categories of perfect modules. Okay, so even though these finitely many Venn cycles is in principle, this is a much simpler problem. In some sense, up to formal completion, it recovers the entire Fukaya category. So this Fukaya category is defined over K. Okay, and this has certain implications, which are silly algebraic implications. Here you go. Okay, so suppose that this BQ has a model defined, excuse me, I'll be right there. Okay, defined over R in CQ. Okay, then the full subcategory of M bar consisting of rigid objects has a model defined over the algebraic closure. 1 second, I'll be right there. Closure R bar inside K. All right, question?
No, I mean, remark Fukaya of M bar, yeah? You missed some.
Oh, I'm sorry. Yes, thank you.
There are graduate students here. So
yeah, I'm sorry. My mistake. Of F of M bar consisting of rigid objects. Okay, so
what's the ring of the formal Laurent series?
Oh, some ring, any ring.
Mm-hmm. And when you say algebraic closure, that means just the algebraic integers inside of the K.
Well, K is an algebraically closed field.
That's right.
So I just mean the closure as a field, algebraically closed field. Okay.
See, so it's not all the R bar.
It's not the integral closure.
The field, right?
Yes, it's not the integral closure. It's the actual closure. You pass to the quotient field, and then you do the algebraic.
Okay, thank you. Yes.
So sorry. I haven't finished explaining this. So first of all, I have to say what this insistence of has a model defined over. This is slightly harmless. So the Fukaya categories are chain level objects. So they're in no way unique. Okay, so in that sense, you could say, if I ask what functions of Q appear in the Fukaya category, you can say, well, that's a pointless, meaningless question a priori, because the Fukaya category is only well defined up to quasi-isomorphism, and who knows, you define it in your way. You got some weird functions of Q, I don't. So the correct thing to ask is, among all the possible quasi-isomorphic representatives, is there one that's defined over a smaller say, ring of field. Okay, so here I'm supposing that for BQ itself, just these finitely many vanishing cycles, you can make a choice of how to define the Fukaya category, which defines it over some smaller ring. Let's say instead of all power series in Q, you just have one polynomial in Q and the ring that it generates. Could be, right? So this has an implication for the Fukaya category as a whole, not for all objects of the Fukaya category. As I said, a general object of the Fukaya category is some Lagrangian with some local system that you can choose in a widely varying way and you cannot control it. But objects that are rigid, which means have no infinitesimal deformations, no first order infinitesimal deformations, are always defined over the algebraic closure.
So does it mean in terms of the mirror, that mirror dual to this subcategory, it's not just a non-Archimedean something, but has a model or the same algebraic closure?
That's correct.
Okay.
To the extent that mirror symmetry
yeah, I
is
mean,
true. So I want to make this a little bit more concrete, what it would actually, what would the implications be, okay? Because, it still says there's a category, model category, okay? Okay? So suppose we know this. Okay? And so let me take just a, and that, say the complex dimension, this is just an example, okay, to make sure what does this mean concretely, okay, is divisible by 4. Okay, so take some Lagrangian submanifold in M bar such that, for instance, let's say H1 of L is 0, H2 of L is 0, H3 of L is 0. Okay, and well, say H4 of L is one-dimensional, and H5 of L is 0 for simplicity. Okay, and so then L is becomes an object of the. I'm using all these vanishing things. It's uniquely an object of the Fukaya category, which is rigid. And so the endomorphisms, so usually the endomorphisms in the Fukaya category are a chain complex. But what I want to talk about is the homology, which is usually called the Fluorochromology. Okay, it satisfies, well, HF4 of LL is just the ordinary cohomology, so it's one-dimensional. And there's also the top dimensional, which is also one-dimensional. Okay, so these endomorphisms of this object are a ring. Okay, so we can look at, say okay, so I have this Fluorochromology here, and we have the n over 4th power. So just compose the powers of this endomorphism. You end at an endomorphism of degree n. Okay, and remember, both of these are one-dimensional. Okay, so if this is non-zero, oh, I'm sorry, this is not right. I want this one here in degree 4. I want this to be two-dimensional. Okay, so in degree 4, this would be two-dimensional. The reason is because there's a spectral sequence going from ordinary cohomology to Fluorochromology, but I asked for the ordinary cohomology to be 0 in the degrees adjacent to 4, so it has to stay. And the top dimensional one will be one-dimensional because that will be actually the the top dimensional cohomology. Okay, and I think I survived this mistake here. Okay, so if this is non-zero, its vanishing defines a divisor of degree n/4 in the projectivization of HF4. So you say, when is this 0? Okay, so this is P1. Well, a priori it's P1 of K. Okay. So then, if we know BQ is defined over R, this divisor is defined over R. Okay. So in other words, you have the, you think of these points, so elements, so inside HF4LL, it's 2-dimensional. There are certain 1-dimensional subspaces where the n/4 power is 0. And so these give you a point. A priori, this could be any collection of points with multiplicity inside this projective line over K, which you can think of it as a collection of points that move independent of the parameter Q. Okay. And so then if it's defined over a smaller ring, then really the points are constrained in how they can move. So you take 4 of those points, you compute the cross ratios, and you get something that lies in R bar. So this is a concrete consequence. So you can take some object. I made a bunch of assumptions to simplify this argument here, right? Okay, you can say, well, I never wanted to look at these kinds of Lagrangians, but this is just one of the concrete things. You take an object, you look at its Fluorochromology, its ring, and this kind of defined over a smaller field has concrete implications for that. Okay, and I should say this lemma here is sort of EGA style algebraic geometry. Okay, so if you look into EGA, it has a number of theorems that say, if a variety is defined over Q bar and it has a complex point, then it has a Q bar point and so on. And these are the same kind of arguments here. It is easy, easy algebraic geometry, very easy algebraic geometry. Okay. So this is so far, all I've said is I've tried to make clear why, instead of looking at the entire category, it is okay to look at this subalgebra given by this subcategory given by these finitely many vanishing cycles, why that, and if we knew something about that, what implications this would have. But I haven't actually done any work. I haven't stated any theorems. Are there any questions?
So it's all about rigid objects only, yeah, kind of.
It's all about rigid objects, because a non-rigid object, will have its own moduli space, and most points of that moduli space are not defined over anything smaller.
In terms of algebra, yeah, probably you're right, but there are some nice classes of divergent series which are now in fashion, like resurgent series, and it's still smaller, something smaller than just Novikov field. Yeah.
No, that's a question. That's a question about rigid objects. I haven't said anything about what I think R would look like, right?
No.
Okay. Now there are certain cases where we can use mirror symmetry to actually obtain this kinds of statement. Okay. So let me look at an example here. Okay. So this is the simplest. This is the most classical example. You take a Calabi-Yau hypersurface. In projective space. Okay. So then the mirror think of it as some kind of orbifold. It's also an orbifold hypersurface, Calabi-Yau hypersurface. So there isn't really any hardly any point for me writing this down here, but and so divided by some group. So which means you work equivalently with respect to that group. I'm sure I got at least one of the indices wrong here. So this depends on the parameter t. So in the sense that so if you take the subcategory of dB of x coming from the standard exceptional collection on projective space, made, that's the standard exceptional collection considered equivalently, okay, on projective space. Then this is quasi-isomorphic to this BQ up to a change of coordinate, right? Which let's say t equals f of q. Okay, for some f of q, well, equals alpha q plus O of q squared, some power series, okay, alpha not 0. Right? So this is the famous mirror map. Now you observe the following thing. So of course, dB of x is actually here. So when I say this parameter t, so a priori in mirror symmetry you would treat t also as a as being a formal parameter, as being formal power series in t, and t equals 0 is the large complex structure limit. But this one would have wrote down that makes sense for all values of t. Okay, so that's actually defined over C bracket t, hence leads to a model of BQ defined over C bracket f of q, sorry, C bracket, no, yeah, inside. Instead of having arbitrary power series, you'll just have polynomials in T, where T is f of q, so polynomials in f of q. Okay, and so so of course this one here, right? So this is the homological mirror symmetry statement. A la Sheridan, this is Sheridan's theorem, and then once you get here, the question is, well, what is this mirror map F? So the standard answer is to say that Hodge theory, well, non-commutative Hodge theory maybe, determines the inverse, meaning Q equals F inverse of T. Okay. All right. So let me try to say again what the process is here. Okay. So this gives you a result where you get an actual a sub-ring of formal power series, which is a polynomial generated by a single power series, f of q. Let me say again what the process is, okay? So the first part of the process is that you prove some form of homological mirror symmetry. Typically, this is done by deformation theory arguments. Then the second process is that you observe, and that's a sort of observation that you would have to make again in every single case, exactly what the mirror is defined over. So in this case here, it's very easy. The mirror is defined over T over the whole affine line. So it's defined over polynomials in T. And then, so what happens is that the parameter Q, sort of the canonical parameter, is somehow intrinsically distinguished among all possible parameterizations of this family by certain Hodge theoretic properties. So you can figure out how Q should be written in terms of T and then you invert that. Okay. So from a practical perspective, the disadvantage of this method is that, well, you have to prove homological mirror symmetry, but that's not much so what I mind, even though, there's no chance for us to prove a homological mirror statement that would apply to every pencil of anti-canonical hypersurfaces in every Fano variety. But also, once you have to do this, you have to look at the mirror and see where it's defined over. And until you do that, you won't know what the answer should be. So that is the limitation of this method. Yeah, the thing that gets on my nerves is that the method produces the inverse map of F, but that you may not share my. Okay, so this, by the way, this is this non-commutative Hodge theory characterization is Ganatra, Peretz, Sheridan, following earlier ideas of, well, inevitably Kontsevich and Novikov. And of course, the idea of a canonical coordinate that this is based on comes from classical mirror symmetry and is even older. But so in this case here, yes, go ahead, question.
No, I mean, if I look just at the kind of quantum differential, at the connection, I mean, it's a connection with kind of one regular point and one regular singularity and one regular singularity. In terms of this connection, I mean, sometimes connection can be defined over a smaller field, like in this theory, I believe, Simpson. So, I mean, is it possible to see this smaller ring of definition looking at some at quantum differential equation?
Yeah, so the question is here, what if I didn't look at the mirror, I just looked at the quantum differential equation?
Yeah.
Well, so you write down the equation, but the problem is then, in terms of the variable Q, the quantum differential equation, is a formal equation in Q, right? Yeah. So these other poles that you mentioned, they appear after changing coordinates to T. Then you see that it has, poles at various other properties, and then it becomes a very rigid object.
No, I mean that in the spirit of this kind of same.
I see.
Couple of Maxim Stocky in Miami, that you can look for some loci, not Q does not belong to H2 kind of. For example, if you look for a smaller quantum, a small quantum, not to the whole H2, but to some Hodge loci inside, that you restrict kind of your quantum differential equation and consider not all classes, but some subspaces in the cohomology which already can have information about a smaller field of definition of the mirror. I think that was one of his ideas in this project with Ludmila, I believe.
That's a bit above my intellectual budget, maybe. But I wanted to point out here that here, in principle, I just stick to a single variable for now, right? I just have a single, which is rescaling of a single symplectic class. I don't know how to answer your question. Okay, let me get to actual theorems, okay? All right, so. Where am I? Oh, okay. All right. So, okay. So theorem. Okay. I want to make a couple of simplifying assumptions so it doesn't drive me crazy. Okay. So again, we have just to write it down here. So we have this one here is the Calabi-Yau. And it's assumed to be a member of a pencil. And we have the base locus, which is a divisor inside there. So I'm going to assume that the base locus is connected and that the Calabi-Yau has no one cohomology. Okay, this is in higher dimensions. This is essentially automatically satisfied. I don't want to waste any time on this. This is kind of technical assumptions that make my life a bit easier. Okay. Take the second Betti number of the Fano in which M lives, because if it's high dimensional, this will just be the second Betti number of M bar minus 1. Okay, so then there is a model for BQ defined over, okay, so you have a function f, and you have a bunch of auxiliary functions in the inverses. So here, f of q is a q plus O of q squared, and G1, GR are invertible elements of CQ. They are all explicitly given in terms of Gromov-Witten theory. Okay, so the simplest case would be that you start with a Fano variety which has B2 equals 1, in which case R is 0. So in that case, the result is the same one as we saw in the case of projective space, is I give you a single function and the single power series, and the polynomial sub brings the polynomials in that power series. That's where it's defined over. Okay. In the general, you have these auxiliary functions G1 and the inverses, GR and the inverses. I am not making any prediction about the structure of the subring of power series that they generate. All I'm saying is, take F, G1, G1 inverse, GR, GR inverse, and take the subring that they generate. That's what this bracket means. Whatever the structure it is, it's defined over that. And moreover, these functions are all explicitly given in terms of Gromov-Witten invariance. So if you're interested in, for instance, can you make a model of BQ which is locally convergent in Q, it turns into a problem about Gromov-Witten theory, which I'm not a Gromov-Witten theory person. You have to solve for yourself. So this is a bit different from what I was talking before. It's a completely general theorem. It doesn't use mirror symmetry in any way, other than these, pretty weak topological assumptions. It uses the fact that we have a Calabi-Yau hypersurface in a pencil of such hypersurface on a Fano variety. That's kind of crucial. But otherwise, it doesn't use anything. It also has a certain disadvantage, which you can try to compensate, which is, if you look at this previous argument, this non-commutative Hodge theory produces the function f. You don't have to do any extraneous information. In fact, it predicts the Gromov-Witten invariance, doesn't use them. This one here is different. There's an external input, which is this Gromov-Witten invariance, into this statement. And okay, so this is a bit in terms of Gromov-Witten theory. And in fact, this is a fairly qualitative statement. It says there is a model defined over, but the actual precise form of that statement gives you a model with very, very specific properties, of which this is just a fairly weak consequence. And so it boils down the amount of computation you have to do in order to compute BQ to a very small remaining amount. Right. So this is the theorem. Yeah. So the proof of this, sorry, the proof is about, I don't know what, 500 pages long. And so it's hard for me to give a talk about the proof. In fact, there's no given moment in my life where I have all the details of the proof in my head simultaneously. But what I would like you what I would like to tell you is, I would like to tell you in my remaining time how these functions exactly arise in terms of Gromov-Witten theory. Not exactly, but at least give you a sort of sketch. The reason being that what's happening is entirely different from the classical picture of mirror symmetry with its Gauss-Manin connections and Hodge filtrations and so on, and quantum connections. None of this plays any role here whatsoever. Okay, so how do I get these functions? And Gromov-Witten theory of what? That's my first thing. Okay, so starting from our Fano, in which I think we can blow up the base locus. Okay, to get a Calabi-Yau fibration with something that has, let me call it E bar over CP1 with smooth, so M bar is the smooth fiber. Okay, sorry, so this deserves, so this contains M bar as a smooth fiber and the exceptional locus, which I will call delta E. So it's just that, the thing that happened after blow up. So it's CP1 cross the base locus that you blow up, and it sits in every fiber of this fibration. Is everybody good with the geometry here before it disappears? So the simplest case would be if I started with a pencil of elliptic curves in CP2, it has 9 base points, I blow up 9 base points, and I get a rational elliptic surface, which is this E bar over CP1. And in this case here, it would contain CP1 cross 9 points, which would be this exceptional locus. So let me take the second cohomology of this. What am I even doing this? Second homology, which is integral homology, more torsion. Okay, so this is, if I counted my R's correctly in what I said before, this is R plus 2. And so this is an abelian group. It has a bunch of sort of filtration and so on. And we associate to it a multivariable Novikov ring. So, okay, so maybe I should have said before I go off into the details. So the Gromov-Witten invariants that appear in this theorem are Gromov-Witten invariants of E bar. And they're not Gromov-Witten invariants of the actual Calabi-Yau that we're looking at. In fact, rational curves that lie inside the Calabi-Yau don't actually appear in this at all. So we associate this a multivariable Novikov ring, okay, which I call lambda. Okay, so say an element of lambda is, you have some kind of series, I will not be precise about the conditions here, which has, well, what am I even doing here? Q to the A. So these are formal variables, Q to the power A, for A in the second homology. And the coefficients, let's say they're complex coefficients. Okay, so this is a multivariable, so which comes with a, if you wanted to collapse back, okay, so into a single variable, say field of Laurent series, you would take this one here and you could map it. Well, you should take the kind of integral of the symplectic form over this. Now there are various choices of symplectic form. Let me just take the intersection number with the exceptional, well, with the exceptional divisor, which is not an ample divisor, but it very nearly is, and it's enough for my purposes here. Okay, so there's this kind of collapse map, and this is important that you remember this, because afterwards I want to make a statement about functions of a single variable q, so I'm going to collapse everything back. Okay, so the reason why I introduced this Novikov ring is because this is the natural thing that you count Gromov-Witten theory in. Okay, so take the Gromov-Witten invariance, counting curves of genus 0 in E bar, whose projection to CP1 has degree 1 or 2. So in the case of degree 1, you could call them sections if you wanted. Okay, so this gives you two different invariants. So you look at the sections and you look at the subspace, the cycle in E bar that they form. So strictly speaking, it's a Gromov-Witten invariant with one mark point. And it gives you, so these are the points in E bar which lie on one of those sections. They are of complex codimension 1, real codimension 2. They give you a class in H2. And you distinguish between the different homology classes of sections by counting the things with these formal symbols q to the power a. And okay, if you consider these kind of things that have degree 2, you could call them bisections, not sure then generically through every point, there could be one of those. That's how the dimension is. So this one here just gives you an element of your Novikov field. Okay. All right. So what I've introduced is I've introduced a multivariable Novikov ring, and I introduced two very simple Gromov-Witten invariants of E bar. Okay. One is just simply an element of lambda. The other one is a class in H2 lambda. So it's a bit of a question what actually I'm going to do with this. So what I'm going to do with this is I'm going to construct a derivation, something like a vector field, okay, which takes q to the a. So you take the b coefficient here of, so this is b in h, okay, so it's a second homology. You take the corresponding coefficient of this, which means you're looking at sections in class B. This is a class in H upper 2 of E bar with, I don't know what, rational coefficients. You pair it with A, so that's now a number, and you do Q to the A plus B. So this is a derivation of lambda. You can think of it as a vector field, okay? So the functions f, g1, gr in the theorem are obtained as follows. Okay, so roughly speaking, there are various other constraints that get them more precisely. So you take elements g1 tilde, gr tilde of lambda with which satisfy this one here. They are a constant in direction of this particular derivation. Okay, and there's a certain space of such element, and you pick more or less like a basis, and then you generate this G1, GR by collapse. Collapse means what I said before, where you take the multivariable Novikov ring and you reduce it to one variable. Okay, so okay, maybe it's useful to have a geometric picture here. So in fact, these are not, these are, in some subring here. And if you wanted to think about it geometrically, you could think about it as follows. You could think of this lambda greater equals 0 as a kind of speck of something and a speck of what it would be. So there would be, I don't know how to draw an algebraic torus. So I'm just going to draw a torus. So this would be an algebraic torus. So think about this as C star to the R minus 2. So these are R minus 1, excuse me. And you can think of this lambda greater equals 0 as a kind of formal thickening. Okay, so spec lambda greater equal to 0. If you think it should be R instead of R minus 1, I agree with you, but I have certain details that I'm sweeping under the rug here. So this derivation that I introduced, dz1, it's a very, very nonlinear vector field, but it's a vector field on this formal thickening that transfers to this to the original algebraic torus. And so therefore, if you have a function, a polynomial on the algebraic torus, there's a unique way to extend it in a covariantly constant way over the deformation. And so you take functions which are sort of generate the ring of functions on the torus, that's why there's GIs and their inverses, and you do this covariantly constant prolongation, and you get these functions that appear in the theorem. The function ff is a lot more interesting, okay? So remember, so I've used two Gromov-Witten invariants. I've used Z1, but I have not used Z2. So of a certain third order highly nonlinear differential equation in which Z2 enters. Okay. So this is an equation, well, it's actually an equation in here, but all right. And then you collapse it and you get F. And so the question is, what is this one here? So 8 times Z2 is just an element of this lambda, so you can multiply it by A. So, okay, so this one here is a Schwarzian. Okay, so remember the classical Schwarzian is, okay, so it's a Schwarzian, you apply it to some function here of one variable, and it's f prime prime over f prime prime minus a half f prime prime over f prime squared. This slightly mysterious nonlinear third order differential operator. So here we use the same, but with dz1 instead of differentiation. So you can make a Schwarzian operator based on any derivation that you like. Okay, assuming that it has to act on functions so that you can form these quotients f prime prime over f prime. But I'm not going to explain that now. So this is so in other words, the functions g1 up to gr come from these multivariable functions, which are solutions of a very simple first order differential equations involving Gromov-Witten invariants. This one here is in principle the same. It's a solution of a differential equation involving Gromov-Witten invariants, except that the differential equation uses more Gromov-Witten invariants, and it is a much more complicated differential equation. So I've not been entirely honest about the conditions, exactly which solutions f tilde do you want. But that would take me a little bit too much time. The outcome is that it's sufficiently unique so that it actually determines this ring here in the theorem. So, I can't tell you whether you should take f or 2 times f or f plus 1, but that's kind of irrelevant because they would all give rise to the same subring. Okay, just in terms of status, so this is an announcement of a theorem. In the long series of papers that lead up to this, there are 3 missing at the moment, but I hope that I understand all the details that enter into this, I hope, and I hope that in the fullness of time, the proof will actually be completely distributed and published. Okay, I will go back to this and, oh, I should probably do, I'm sorry, I have a couple of minutes left. Maybe I should do an example, right? Because you're all horrified. So the simplest example in the world. Okay, so it's okay. So the example is so a pencil of cubics on CP2. Now you'll say, well, hold on. There were certain conditions about H1 being 0 and H1 of an elliptic curve is certainly not 0, but that's a technical question. If you have an example like this, I can work around this part of the argument and so get something that can apply to this. So the Schwarzian, so in this case here, there's no G functions. So the Schwarzian equation, well, you can write it as a Schwarzian equation for a differential involving Z1, but it's equivalent to an ordinary, is equivalent to, it actually turns out to be quite simple. So this is the classical Schwarzian. And there's an Eisenstein series. Which is there's a eta function okay. So so this one here, by the way, so 1 over f, if I was how did I do these computations? Well, they're all modular form computations. So this is a Hauptmodul for gamma 0 of 9. And once you know this, it's you know, the Schwarzian derivatives of Hauptmodules, you know, that's a classical subject in modular forms. So it's easy to solve. And of course, this agrees with the classical mirror map, or rather the classical mirror maps write Q as a function of an auxiliary parameter. So this is the inverse function, and it agrees with that. So that gives you, that of course, from a geometric point of view is sort of pointless because we know everything about the Fukaya category of an elliptic curve anyway, but it just proves that the method works. And that's all I have to say.
Thank you very much. Questions, please? Okay. I see some upload, but it's not a question. Where the rigidity is hidden in all this?
You mean the rigidity of objects?
Yep.
No, that's just a question of applications. So once I know that BQ is defined over something and I want to apply it, the natural application is to rigid objects. I mean, you know, BQ being defined over something just gives you a statement about these particular Lagrangian submanifolds, which are the basis of vanishing circles. But suppose that you don't give a shit about those, then the larger class you could say something is rigid objects. But that's entirely separate. It's just the application of this. You can ask me questions. I'm a non-intimidating person. Please, graduate students, everybody.
Okay, so graduate students, or even former graduate students, maybe.
I think I qualify that.
Okay.
Can I ask a so how does this work? So you've got this moduli space of disks that intersect this the space locus, and there's some these differential equations come from some sort of action of what, the quantum cohomology, or like something like this, some closed string action on these moduli spaces.
Gosh. Okay, let me say it like this. So the first observation, which actually goes back to Aru, Katsakov, and Orlov, which is generalized here, is that if you set up things correctly, there is something else, which is the Fukaya category of the actual fibration, Lefschetz fibration, that is actually independent of there's certain direction in the Kaehler moduli space where you move in that direction and the Fukaya category doesn't change at all. Okay, and there's a reason for that coming from sort of open, closed, open string maps. That is step number one. And that direction is identified by the Gromov-Witten variant of section Z1. That's where that comes from. Now you can say there's a certain relation between the Fukaya category of the Lefschetz fibration and the Fukaya category of the fiber. So you have a certain direction in your parameter space in which the Fukaya category of the Lefschetz fibration does not change. So what happens if you try to analyze the change of the Fukaya category of the fiber in that direction? That requires looking very closely at the relationship between the two, and that's why that second part involves this horrible Schwarzian differential equation, and it's kind of complicated. The idea is that the mirror of this situation is also fibered over CP1. And fundamentally, I'm trying to recover f of q is the linear parameter of the mirror would be. And so therefore, if it's a linear function, if I differentiate it twice, it should be 0. But it's not using mirror symmetry. So I had to set it up the whole thing in non-commutative geometry to be a counterpart of that. And that's kind of the complicated part. So up until the Fukaya category of the Lefschetz fibration is constant in direction of Z1, it's a relatively simple formal argument involving open closed string maps. And then things become a little bit involved. There's a hand up, Rina.
But it's not entirely a statement of non-commutative Hodge theory. You need kind of...
It's not non-commutative Hodge theory, it's non-commutative geometry. So it's a question of what does it mean for something, for the mirror to be fibered over CP1 without using mirror symmetry.
That's interesting, yeah. Gabe, are you happy with the answer?
Yeah, I think that's going to get me as far as I can go.
More questions?
Rina, do you have your hand up? Oh, no, sorry, that's my mouse pointer. Okay, even basic questions, graduate students, I'm happy to answer. Things that have, not directly related to the talk.
So in this example you wrote down, right? You'd get something about Fukaya category of an elliptic curve, which
yes,
is not much new to know. But so if you do this for like a quartic or something, would you get, like following your lemma, like discover something about objects in the, or rigid objects in the Fukaya category that we didn't know?
Well, remember for Fukaya categories in CPN, for Calabi-Yau hypersurfaces in projective space, I did it using mirror symmetry before, right?
Yeah.
So I did the example of the quintic threefold, and I checked that my mirror map agrees with the ordinary mirror map up to order 40 or something. But I am really not a quantum Lefschetz type person. I have not tried. This can be done, this computation of this Z1 and Z2 can be done in a ton of cases just using quantum Lefschetz. For the quartic surface, again, there's modularity properties of the mirror map, and they also appear here. So, I mean, you're not going to get anything new about the mirror map because it's supposed to be the same, even so why it is, it's a complete mystery. But you get a much stronger statement because you get a statement of definition of the Fukaya category. I'm mostly interested in applying this to cases where you don't know mirror symmetry, or you don't know where a mirror exists. But unfortunately, those cases tend to be kind of hard to do explicit computations in. So for now, it's a more like in principle statement.
Okay, so what would be the easiest example for which mirror symmetry would have the statement about this mirror map? Would be enough?
Well, you could take a Calabi-Yau hypersurface in a Grassmannian or a flag variety. In principle, we know the mirrors, but in practice, homological mirror symmetry hasn't been proved to the extent that I am up to date these days.
Okay. Thank you.
I have a very basic question. You mentioned about the multivariable Novikov fields. So can you say a little bit how the ordering or the convert, say the going to infinite in what sense?
Can you ask that again? Sorry.
The multivariable Novikov field. So you suppose you have two variables, and how is that Novikov field defined?
Oh, the multivariable Novikov. But it's not a field.
Right.
If I said field, that's a horrible question. So
I see. So it's only a ring.
So it's a ring, yeah. So sorry, maybe I said field. It's really a ring. So it's the ring of this series here, and you complete it in a certain direction, which is say the intersection number. You're allowing an infinite sum, provided that these A which occur, the intersection number with the exceptional divisor goes to infinity. Okay. It's a ring. It's not a field. I apologize if I said that wrong.
So in this case, you complete in giving some kind. Suppose H is that's a abelian group giving a cone.
That's well. It's yes. It's a cone. It's actually a half space in this case. Here, it's very simple. You have a homomorphism from H to Z, which is given by intersecting with the homology class of the exceptional divisor, and you just complete in the direction where this goes to plus infinity. So it's actually a very simple completion. The cone's a half space.
Okay, thank you.
So Paul, just to clarify for myself, so kind of the key thing which you need in order to everything work, that you should have a family over CP1.
A Lefschetz pencil. You start with a Lefschetz pencil.
And so that's okay. All right. Okay, more questions? Last chance. Well, graduate students are silent, so all professors have already asked you questions. Well, let's thank Paul. Thank you very much.
It was a pleasure.
Interesting talk. And then this is it for today.